The first physics concept we want to look at is the idea of work. And work is a measurement of the change in energy on an object or a system. So I want to take a minute just to talk about energy first, but that's where we're headed. We want to look at this idea of work. And work is change in energy. So you have a system or an object, you apply a force to it, you'll add some energy or possibly take some energy away from that object or system, and we're going to be interested in measuring that change. So first of all, what do we mean by energy? We usually think of two components to energy. An object or system will have a portion of that energy is what we call kinetic energy, and a portion is what we call potential energy. Kinetic energy is the energy that that object has due to its motion. So when you're in motion, you have some energy inherent to that. And then potential energy you can think of as energy that is stored and is available to the object to be converted over into kinetic energy. There's many ways that energy could be stored. We will be interested in two types of potential energy. One, gravitational. So if you have an object sitting there on a shelf and you knock that object off and it falls, it starts to move, it starts to gain kinetic energy. And really what it's doing is it's taking its potential energy. By being up on a shelf, it had the potential to fall down to the floor. So that gravitational potential energy you can think of as a reserve it has at its disposal to turn into kinetic energy. So gravitational. Mechanical is the other one we'll look at, and specifically we'll look at springs. So if you just have a spring sitting on a table, not attached to anything, it has no kinetic energy because it's not moving. And it's got no potential energy in terms of mechanical because it's not going to all of a sudden start oscillating all on its own. But if we push that spring in or stretch it out, we've now charged it up with potential energy, mechanical potential energy, because as soon as we let go of that spring, it'll start oscillating in and out. It'll turn that potential mechanical energy into kinetic energy. So we're going to be interested in mainly just the change in this part. Our systems will not be moving when we start, and they will not be moving when they end. So the change in kinetic energy will be nothing. So really what we're going to be calculating in our work calculation is specifically just the change in potential, because this contributes nothing in the stuff we're looking at. So a couple of notes here. Even though we won't be dealing with kinetic energy, just for reference, kinetic energy is 1/2 mass times velocity squared. So if you wanted to calculate the kinetic energy, this is the formula for that. We won't really be needing that very much. But for potential energy, now that varies. Depending on whether it's mechanical potential energy, gravitational, those are the two things we'll look at. But there's other types of potential energy. There's chemical potential. There is nuclear potential. So we have various ways that energy could be stored. We will be specifically interested in the computation of gravitational. And that's just mgh, where m is mass, g is that g we saw, the acceleration due to gravity, and h is the height. So one thing to note here is that when something, typically, we are not going to be altering the size of the Earth in any of our problems, so g is fixed. The object's mass won't change. So these two things really taken together are just the weight of the object, right? Mass times acceleration, and this particular acceleration is gravitational. So really we're looking at the weight of an object times how high up it is. That gives us the gravitational potential energy. Really all we're going to be playing around with is the height. So by moving it up, this value increases. That change in h results in a change in potential energy, which means work. So in our gravitational problems, really what we'll be doing is affecting the height and looking at what that did to the overall energy. Okay, so what about units here? First of all, we could look at these here, but this is really only true for gravitational. So I want to look at work from a computational standpoint. Conceptually, it's change in energy, and I think as we work through these problems, you should keep referring back to that idea that we're changing the energy, and that's what we're really measuring. But computationally, you can think of work as force times displacement. So force, as before, that d now is displacement. Displacement. So if you apply a force to an object and apply it over some displacement, so push a chair or whatever, that thing will start to move. You'll add kinetic energy, right? Slide a chair across the floor. You will have pushed on that thing, applying a force over some displacement of your arm there, and you will have put some kinetic energy into that and caused it to move. For us, the force will be, for example, here in gravitational, look at that. Potential energy is a force times a distance, right? The gravitational force times the height. So there's your force and your distance. So what does that mean in terms of units of energy? So work is change in energy. So work is a type of measurement of energy. So the work units should be energy units. So what are our energy units? Well, force times displacement is an easy way to think of it. So our force units in the metric system, force was in newtons, and distance was measured in meters. So energy units are Newton meters. And just like the kilograms, meters per second squared combined all together to be called a Newton meter combines together to be called a joule. So 1 Newton meter is a joule. So our energy units are joules, or you could say Newton meters, they're equivalent. And then in the imperial, we had pounds, and distance was in feet. So when you multiply that together, we don't have a fancy name for it. It's called a foot-pound. So a pound times a foot is a foot-pound. So our units of energy, in that order, it's typically said as a foot-pound, not a pound-foot, but so foot-pound there. So these are our energy and therefore work units in the imperial system. Here's our energy and therefore work units in the metric system. And so typically, the work calculation, if all we were doing was just moving an object, a solid object up, it would require no integration. But if the object changes its shape as it moves up so that all the mass doesn't move the same distance, then this is going to require an integral. So we'll look at that in the gravitational, and we'll look at springs. We'll look at storing energy by compressing or stretching a spring.